Good afternoon, everyone. My name is Sana Zorandi. I am the PRIF manager, and I will be your MC for the last afternoon session. For our next talk, we welcome back Ben Koch from the panel discussion. Ben has found participating in PRIF as a valuable experience. It has helped him better understand how to integrate advanced technologies with practical applications in the mining sector. Working with academics experts has given him new insights into the latest research and innovations, and it has improved his knowledge of how artificial intelligence can improve ECO's software. His greatest achievement during PRIF has been leading a cross-functional team in the development of a high-resolution 3D model for stockpiles. The project has the potential to greatly expand the reach of ECO's stockpile management software. Ben believes knowing their research collaboration come alive and grow, and it can have a positive impact on the mining industry, has been rewarding. Welcome back, Ben.
Thanks, Sanaz. Hi, everyone. Today I'm going to share my, reflections on the PRIF project, and in particular, presenting what I've entitled "Optimising Stockyard Management: Industry Insights and Academic Expertise," focusing on our work with Translation Project 4, ROM Stockpile Modelling. And that was done in conjunction with Research Project 5. So I'll start with a bit of background about ECA and how we came to be involved. ECA is a global leader in commodity management software. We offer a comprehensive suite of tools designed to streamline and optimise management of raw materials and commodities, from aspects involving the trading desk to the factory floor, risk management to automation. Of relevance to the PRIF Mining Consortium, ECA's stockyard management solutions are at the forefront of industry innovation, offering 3D stockpile management, so real-time stockpile modelling for the precise control of shape, volume and quality, enabling optimised stacking and reclaiming, and quality management, advanced systems to trace material quality and optimise blend management, ensuring delivery to specification. We have a rapidly growing client base across multiple commodity segments, with over 100 customers worldwide, including many large mining companies, and we operate Americas, Asia, Australia and Europe. ECA's involvement in the PRIF Mining Consortium marks the latest chapter in nearly 20 years of academic partnerships that I've been involved with, starting with some more simple things like sponsoring masters onto PhD projects and so on. This project, however, has been by far our most intensive and challenging collaboration to date, exemplifying the profound impact that academic research can have when applied to real-world commercial outcomes, and I hope it stands as a testament to the power of combining the academic rigour and industry expertise to achieve significant technological outcomes. So, early in the project, we had the opportunity to visit the Prominent Hill mine site. This was operated at that stage by Oz Minerals, now BHP. The visit was particularly valuable for all involved. It was the first time that many of the researchers had experienced a mining site firsthand, and I think we've heard from a number of speakers and perspectives that today that's a really important thing. And the ECA team, who was familiar with these things, also gained insights into a different type of operation than was typical of our existing installations. For me, visiting underground at an active mine site for the first time was definitely an unforgettable experience. During our stay, we met with various operational teams and tried to identify, well, we did identify 3 main challenges in the ROM yard. So the ROM yard's the large area towards the top right of the screen here. These challenges were, number 1, grade variability. So issues with variable mill feed due to limited visibility into grade variations within these large stockpiling areas. The available data was typically available at a weighted average level over time with no information or ability to pinpoint specific spatial locations of different grades. Number 2, traceability. So difficulty in responding to emerging problems in the plant. So there was lack of location information about where current feeds were coming from to help correct for problems being observed downstream. Additional challenges noted were finding out where material from underground had ended up in the stockyard. And an example that sticks in my mind was sometimes they have to find where a missing bogger tooth or other piece of machinery may have ended up, and it's quite a laborious process at present. Number 3, planning. So essentially the management of the yard and loader task assignment was based on rules of thumb, aimed to minimise variability and then reactively respond to issues as they occurred. Something's gone funny with that image, but that's okay. So with the site visit complete, we presented our understanding of the challenges and proposed solutions to an end user or some end users from Oz Minerals to confirm our approach. The primary objective of Translation Project 4 was determined to be to enhance stockyard management processes in the ROM stockyard by building a near real-time, high-resolution 3D model of the ROM stockpiles. Some specific goals, or the main specific goals, were number 1, developing a fine-grained 3D model, which was to help improve the mill feed predictability. Number 2, optimising the blend planning and execution through an automated planning tool. Number 3, enhancing the traceability for contaminant tracking by correlating sources, being able to correlate sources to destinations for movements within the stockyard. And number 4, providing improved data sources to help enable better data correlation for the downstream mill feed optimisation projects. As is the, I guess the whole mode behind the PRIF, it's a collaborative approach. So ECHA has substantial expertise in stockpile modelling and quality tracking. However, in the past, this has primarily been focused on fixed rail, automated stacking and reclaiming machines. We'd never applied this expertise to a ROM yard scenario where they're using manually operated front-end loaders and trucks. And we also lacked in-house expertise in artificial intelligence for planning and optimisation, or planning optimisation. Through the PRIF Mining Consortium, we were able to collaborate with academic experts in the relevant fields, including PhD and postdoctoral researchers, working directly on the problems we had identified. We determined the combination of industry knowledge and academic expertise would be focused into 4 key research areas. 1, we needed to process the existing data sources, in particular the GPS and vehicle fleet data, and process the data to determine the key activities on locations such as truck dumps and pickups. We needed to, number 2, develop simulation models to simulate front-end loader and dump truck operations, which would then be able to use to feed the planning and optimisation AI systems. Number 3, mapping and adjusting real-time models. So the GPS data lacks certain details, and so the simulated or the real-time models were predicted to drift over time. So the ability to correct stockpile model periodically for errors using survey information was the third goal. And finally, optimising, and the key point of it all, optimising the stacking and recovery programs, a significant challenge given the unstructured nature of the stockyard and complex data processing required to determine the outcomes of the various scenarios. With the objectives and approach determined, it was on to the development phase. The Consortium, fairly early on from memory, decided to use a technology readiness level, or TRL, as a common measure across projects, which is something you've heard, I think, a few times today. This approach helped focused efforts and provide a more objective understanding of progress across the various projects. I guess our journey through the TRLs as we learnt how to apply them. The initial research and development of theoretical models moved quickly. Engineers could help frame the problems, and researchers could apply theoretical techniques, progressing through the TRL 1 and 2 stages rapidly. Proof of concept models for individual components were built, showing promising results on test data, advancing through TRL 3 and 4. Where things started to become more difficult, increasing through TRLs 5 and 6, integrating systems together to demonstrate solutions in a production environment has been slower than anticipated and required significantly more effort than the earlier stages. So the team is currently in the, hopefully, later stages of preparing or integrating the research into our software system. Sorry. So here's just a brief video of some of the testing they've been doing. It shows the survey data imported, the tracking of the vehicles, drilling into the ROM stockpiles. We can see all the various truck dump locations, and slice and dice this data in various ways. To help solve all of those positional traceability problems. And then, of course, we combine that with the data from the lab that correlates back to the grab samples taken underground, and that can therefore project out zones of different gradings and quality within the ROM yard. So some learnings. Upon reflection, there's several ways that we could improve the slowdown that we face moving to TRL 5 and 6. Some of this is a common theme I've heard, and also in Simon's presentation I could see he sort of addressed some of this earlier on, but basically what I can see is academic research techniques differ significantly from production software coding in terms of languages, platform, approach and expertise. Transitioning from a proof of concept, which might be done in MATLAB or Python, to apply it into a multi-tiered .NET application, for example, can be akin to starting from scratch from a software development perspective. Utilising researchers to diagnose problems with a REST API is likely outside of their comfort zone and not the best use of their time. The initial success we achieved quickly had a more minor role played by echo engineers because the work was research intensive. We were running with about a 4 to 5 times FTE allocation to the academic team. When it came came time to move to the proof of concept. Move it to an operational prototype. We increased engineering resources, but hadn't planned or budgeted to do that to the level that ultimately turned out to be necessary. I think, some thoughts on future projects or doing this in future would be to plan for that in advance, make sure, understand that it'll go from primarily researchers to primarily developers as that TRL increases pretty aggressively. Also, I think some reflections on the TRL scale, something that originated in the space industry with NASA, I believe, where moving through the levels is necessarily complex and costly. This runs the risk of encouraging a waterfall project approach, which isn't always suitable for a software project like ours. So taking inspiration from agile practices, which are very common in the software world, would be beneficial. This could mean starting integration and production design earlier in the timeline, integrating different research outcomes immediately as they're available, and maintaining the overall system design throughout, not leaving that to a later stage. All pretty standard stuff, really. In some ways, reasons not to do waterfall. I guess before we conclude, I'd like to take a moment to thank all the collaborators, supporters who've made Translation Project 4, Research Project 5, and possible and helped with our engagement. So thanks to our partners in the PRIF Mining Consortium, the academic experts, PhD, postdoctoral researchers who contributed their invaluable expertise. Name a few of them: Zhao, Harada Simi, Chen-Fu Lu, Marcus Wagner, Frank Newman, Larissa Stasenko. Also, I'd like to acknowledge support from Eka's engineering team, whose practical industry experience was crucial in advancing the goals of the project, Chris Garcia and Paul Elson especially. Obviously, thanks to the Premier's Research and Industry Fund, Oz Minerals, BHP for sponsoring the project, as well as facilitating site visits and providing the crucial data to support the research. The efforts of everyone's been instrumental in the success. So, conclusion. Translation Project 4 has demonstrated the potential for planning and optimising ROM stockyards using data that's already available at many mine sites. So we're not needing to take new measurements or introduce new sensors or anything like that. We're rapidly approaching a production prototype system that will significantly advance stockyard management processes. And the key thing is that the success to date has been achieved through the collaborative efforts of industry, academia, highlighting the importance of combining the practical industry experience with the academic expertise and research. And I look forward to further advancements and future collaboration opportunities. Questions? All right.
So, Ben, could you maybe just summarise the functionality that your soon-to-be production system's going to have compared with your existing system?
Okay, yeah, sure. We do have, I'm not sure, Zhao is talking next, and we'll talk about a bit of his research. But in the context of ECHA, and I guess I touched on it briefly, but what it was about for us is we currently, our stockyard management software currently works in when you've got fixed rail stacking and reclaiming machines. So this is, sector-wise, it works in iron ore, coal, bauxite, large volume ore systems where it's necessary to have that sort of equipment. So what it enables us to do is to use the functionality and features we have in that space in a ROM yard scenario, which from a market perspective opens up, copper, silver, gold, etc. type mining operations.
So paddock dumping and dozer operations.
Exactly. Yeah. Yep. Thanks.
No more questions? Thank you.
All right, thank you.
All right, the next speaker is Dr. Zhao. Dr. Zhao began his research in mechatronics and robotics as a master by research student at the University of Adelaide in the School of Mechanical Engineering in 2007. After completion of his master's, he continued his studies, and in 2016, she completed his PhD thesis entitled 3D Real-Time Stockpile Mapping and Modeling with Accurate Quality Calculation using voxels. His association with the PRIF Mining Consortium began in 2019 with a focus to develop a novel stockyard management system using current mining operational datasets to improve quality control, in collaboration with his industry partner, Koch, and the end-user partner, BHP. His research interests include mobile robot and its applications, machine vision, and control system. She believes he has gained a lot from the PRIF, including responsibility, commitment, and management skills, but most importantly, friendship. The PRIF brought researchers from different disciplines and industry partners together, enabled networks to flourish, and people have become really close. She has made some good friends, and he is hoping to establish more collaborations in the near future. She believes his greatest achievement is the demonstration systems they have built thus far. They have been working together towards this goal for the last 3 years. These two systems not only showcase the innovative solutions they've developed, but also highlights the collaborative efforts and dedication of their entire team. Welcome, Dr. Zhao.
Good afternoon, everyone. In the next 20 minutes, I would like to discuss my project and the outcomes we have achieved so far for the project integration of PRIF extension. As one of the 4 selected projects for the PRIF extension, my primary objective is to create or to integrate the research outcomes from ATP4 and ARP5 by building a demonstration system. This demonstration system can create 4D stockpile models and optimize the reclaiming operations. I will explain why it is called a 4D model in the next slide. So this circle here highlights where the project sits in the entire supply chain. And to begin with, I would highlight the 2 key findings through the integration. First, we are able to generate 4D stockpile models using widely available mine operational data. And a 4D model is essentially a 3-dimensional model associated with the quality information. And these models can be generated and updated continuously during the stacking and reclaiming operations. And we have to integrate the quality into those models, so which means we'll provide accurate calculation results for the quality. And using this data, we are able to optimize reclaiming operations. So to meet the required quality and quantity with 0 or minimal violations on the penalty elements, and also reduce reclaiming time. And this slide provides a very brief summary about modeling techniques. Around 10 years ago, measuring a stockpile required experienced human operators. The process was time-consuming and posed potential safety risks. So this is the reason why one of my tasks in my PhD was to convert a bucket wall reclaimer into a mobile laser scanner and scan the stockpile continuously. Nowadays, unmanned vehicle-based survey systems are widely available, so the measuring process is more efficient and safer. With respect to the modeling process from the measurement data, it has also been simplified. Nowadays, we can simply click the mouse and instruct the software, detect the stockpiles against the ground, and the rest of the task could be completed by the software automatically. However, we are still not able to produce those 3D models continuously. I believe this is one of the major reasons why most stockpile management systems still use tables to represent the stockpiles. A case study about current stockpile management system. First, it is capable to tracing the vehicle movements in real time within the mining site. So the image on the right showing the moving paths of a hauling truck loading materials from the in-pit location and then dump the materials onto the room stockyard. Signal degradation caused the moving paths drift slightly to the right while the truck was underground, but the positioning accuracy was reasonably good when the truck gets to the surface level. And also, we can create 3D stockpile models every half monthly. So the imaging on the right showing the measurement data we received from our end-use partner. And currently, those models are used to calculate the volume of the stockpile. I did a calculation myself after receiving those data sets. So use the RY6 stockpile as an example. Its quality its volume is around 32,000 tons. Given the density, it's 32,000 cubic meters. Given the density, it's 3 tons per cubic meter. So the total material will be around 96,000 tons. If each hauling truck can carry around 220 tons of the material, so roughly it will be 436 truckloads worth of the material in this stockpile here. And clearly, it is not built just by one day, and the quality of each truckload could be different. So to calculate the quality of the stockpile, what people are doing at the moment is trying to use weighted percentage from the quality assay results obtained from the grab sampling process. The table on the right showing the quality assay results. So what happened for this quality assay results is there is normally a delay of 24 to 48 hours. So which means my geologist has to use outdated quality data in the calculation and update the quality of the stockpiles every day. The day-to-day operation changes the quality of the stockpile and degrade accuracy of the quality assay results. So eventually, the effective management and optimization become a challenger. What I was told at the moment about the reclaiming process is rely on the human experts using the room of the samples. So for example, we always understand mix the high quality material with the low quality material, we can achieve the target quality, and also we're trying to maintain the contaminants as close as possible to the required limitations. However, this process is not precise because human planning always have many disadvantages, especially using the inaccurate quality assay result. To summarize, the current room stockpile management system are not able to trace the quality and the quality distributions within the stockpile accurately. And the blending, which refers to the stacking and the reclaiming operations, is less efficient. And to meet the required quality and quantity combinations, it really depends on the chances. From the industry perspective, there is always requirements in improving the blending efficiency and effectiveness, avoiding or minimized price penalties, lowering the handling cost, and reduced emissions. Instead of, we believe, the integration of these two projects will provide a feasible solution to the problems I discussed previously. So instead of creating stockpile models from the measurement data continuously, our industry partner ECHA has a technique to build 3D models from widely available My Operational data set. And these models can be created in nearly real time, can be used as a placeholder for the delayed quality assay results, which is considered to provide the most accurate quality information about our body. And through keyword searching across different data sets, so we are able to mapping the quality information to each truckload. Thus, we can calculate the quality and the quality distributions with great confidence and allow the optimization to be applied either to stacking or reclaiming operations. What we choose here is to optimize the reclaiming operation because of the delay in receiving the quality assay results. There are two demonstration systems in progress at the moment. The full-scale demonstration is built through the Inside CM ECHA software. So the small-scale demonstration is built using self-developed Python program. The biggest difference between these two systems is like the full-scale demonstration is able to produce 4D stockpile models in nearly real time using the My Operational data, while the small-scale demonstration is actually using the survey data. And we have a setup at the back of the stage. We are able to demonstrate both systems live. All the systems are constructed through the identical steps. And the tasks in each step could be slightly different. If we can say there are colored background tasks, which means they have been completed. Otherwise, they are at various stage of the completion. I will detail these tasks in the next couple of slides. With respect to the full-scale demonstration, I reproduced the stockyard from the survey data and extracted truck dumping event and prepared the required information. So the image on the right showing the data we received and the searching strategy is causing these reports and the My Operational data. And so by doing this searching, I can map the quality results to every single stockpile. And during this demonstration system, I create a file. This file contains the truck dumping events and attached with the quality assay results. With some setup, some configurations in the Inside CM software, so we are now able to receive the truck dumping information, the quality information, and the vehicle moving paths. And we can, the next step we're going to do is trying to export those 3D stockpile models and use my MATLAB pods to produce the reclaiming modeling step. This video shows us the Python program we developed to send the API message to ECHA system. So these are the files I produced for the demonstration. They are integrated with the truck dumping information and the quality. All those three types of messages can be sent all in once or one by one separately. So I was trying to send those messages through the terminal, and the response from the ECHA system will be displayed on the terminal as well. So move to the Inside CM software. We can see those stockpiles are created in nearly real-time manner. A close look to this RY7 stockpile, we can see there are some intersections between the dump models. And when we do the quality calculations, we can consider they have multiple layers. The calculation is based on the quality of each single layers. And since Ben just demonstrated, we are able to receive the quality information and also update the moving paths of the vehicles. I will skip this video here. And for the small-scale demonstration system, the geometric modeling is quite straightforward. I use some imaging processing techniques to detect the boundary of those three stockpiles and superimpose those three stockpiles onto the stockyard. And previously, I'm trying to use the moving parts of the bucket to cut the stockpile into voxels. But soon I realized this is not a feasible solution because a front-end loader can attack stockpile from many locations and any angles. So this will result in infinity number of solutions for the voxelization. So I partition those stockpiles into voxels using these 3D grids. And for this small-scale demonstration, I can simply assign the quality information to each single voxel. And these voxels will be converted into a CSV file for the optimization system. The reclaiming modeling for the both full-scale demonstration and small-scale demonstration, they follow the same tasks. However, each node in the full-scale demonstration, their quality will be calculated separately because a node may contain materials from different layers. And the image on the right showing the voxelized result of the nodes I prepared. And for each node, it can be reclaimed from 8 different compass directions. So using those voxels, I produced the precedence constraints, and I can approximately the reclaiming cost for each node based on the volumes, and produce safety constraints for our front-end loaders, and we can estimate the traveling cost for the loaders as well. I use 2 different algorithms to estimate the traveling cost. One is use a computer program to generate moving paths to mimic the real moving paths of the front-end loaders. However, this process is really time-consuming. So in the demonstration, I approximate the moving paths, use the straight lines, so the line connect the 2 centers of the nodes. And this is our small-scale demonstration system. Although it is running on my laptop, but it's actually available to the public through a free web server. However, it could be slightly slower if we're running on this free server. The first section showing us the 3D model and the voxelized results. We can say those voxels have different colors, which represents the volume of each node. The imaging on the right showing the voxelized result of the node CSV file in 2D format. Each node has a unique ID number. This is the reproduce of the node CSV file. We can say there is volume information, there is also quality information. For the optimization system, we have the problem parameters, which is required quality and number of the request, and what is the quantity of each request. And also we have algorithm parameters, including the window size, number of objectives, the greedy parameters, and most of those parameters allow customer inputs as well. So the bottom is the table, and image was showing us the optimized results. When we click this run optimization button, it takes around 4 to 6 minutes to produce such optimization results. And actually notice there is a little bug for some of the reclaiming directions. This is not going to happen in the real time. We're going to fix it once my colleague are coming back. So we can say the material is being reclaimed, and what is the quality for those penalty or desert elements. The animation show us the optimized reclaiming sequences. And those arrows actually show the loading direction or the movement direction of our loaders. So what is going to happen after the conference? Our project ends at the end of this year. So by that time, we're hoping we can finish our project integration. And also my colleague Harald is trying to help us integrate all his optimization algorithms into the demonstration. We have 2 so far, and there is 1 left. And we're working with our industry partner, ICA, trying to seek a chance to integrate the demonstration system into their software suite. And also we have 2 journal papers on the way. That's the end of my presentation. I would like to take this opportunity to express my acknowledgement to my supervisor, Dr. Tianfu Lu, Associate Professor Larissa, and my colleagues Harald and Victor, all end-use partners and translation partners, and the PRIF. Thanks very much.
Is there any question?
So, without trying to open a can of worms, and this question is driven by some of the discussion that happened earlier today about IP, and the answers open to Ben and to Nigel to address as well. What would be the consequences of the PRIF engagement between the university and ICA on some other company approaching you for assistance with their material management and tracking software?
Thanks for the question. This is really out of my expertise. So for me, it's like at this stage, we're still considering ICA will be the best partners for the whole project, but we are open to other discussions. So that's what I'm thinking at this stage. Thanks.
Yep.
You want to comment? Yeah, I think one of the good things that was set up in the PRIF is one of the good things set up in the PRIF, at least from a translation partner perspective, is that for the IP, and I'm not commenting on this from a technical legal perspective, but the IP under Translation Project 4 is somewhat controlled, or decisions are made via the translation partner. So, yeah, without getting into details, I guess my reading of that is that ECA sort of gets the first right of refusal in terms of using the IP developed. I'm not sure if everyone wants to correct.
Well, that's pretty much how it is. Basically, you get first nod, but if you say no, we don't want anything to do with it, then we'd obviously go out. But we are absolutely delighted with the support ECA's given us, and we know that it has placed considerable demands on you beyond what was initially considered over the last year. So that's fantastic, and we hope ECA sees value in this and takes it further forward. Thank you.
All right, no more questions. So thank you.
Is the IP reserved 100% with ECA, or is it shared? Shared.
Okay. Thank you.
Don't go anywhere. Thank you, Shane.
Right, and our last guest speaker for the day is Gavin Yeates, the chair of the PRIF Governing Board. Gavin is an established mining industry leader with over 40 years of experience, including 35 years with BHP. He held various senior roles, executive roles in geoscience, mining, metallurgy, and technology. Since leaving BHP, Gavin consults to mining and metals companies, government, and research organizations. Gavin continues to publish widely on innovations in mining and brings a deep understanding of the mining industry and its professionals, along with a vision for the future of mining. Unfortunately, Gavin is unable to join us in person today and has provided a recording for us.
Hello, everyone. My apologies for not being with you in person as I'm convalescing at home following surgery, but please be assured my thoughts are with you. This conference marks a significant milestone in the finalisation of PRIF. It's time now to both celebrate our successes as well as look to the future to ensure that all of that good work can be leveraged. The PRIF Consortium has met or exceeded all of its major objectives. It has addressed the end-user challenges. It has demonstrated the value of integration along the mining value chain. It has sought to commercialise technologies to both local and global markets. And it has provided research training excellence for higher degree students. As we look back at what made the PRIF Consortium so successful, a number of things come to mind. First, there is the idea of the PRIF. This was conceived well right from the start, and for this we have to thank Steve Grano for his early work and consultation. This idea was picked up by IMA and ISA through the encouragement and strategic thinking of Mike Goodside. The right people were then identified and brought together under a single vision and purpose that crossed both discipline lines and organisational lines. It was so good to see how people coalesced around a common objective, and there was no badges of University of Adelaide versus Uni SA. This only happens when you have good leadership, so credit to Nigel Cook for his overall leadership of the consortium, and to Peter Dowd and Bill Skinner as program leads. Credit also needs to go to each and every researcher who bought into that vision and pulled together both individually and collectively to deliver the consortium outcomes. The PRIF Consortium was set up with the right structure. The role of the mining end user companies to define the challenges, and the METS companies to be the commercialising conduit to take the research outcomes to market for the end users. There was then a governance structure that was set up that was fit for purpose, where a board was made up of both the research leaders, representatives of the end users, the METS companies, as well as state government. My sincere thanks to all of the board members who volunteered their time to provide wisdom and direction to the consortium. I would especially like to call out Ellen Schuller from the state government, who facilitated the most important interactions between the state government and the consortium. This lean government structure has meant that the maximum amount of funds could be spent on research with minimal spend on administration. Finally, a consortium such as PRIF cannot operate without the behind-the-scenes management of things like accounts and schedules and meetings and reporting. This consortium has been extremely fortunate to have Tatiana playing that role very capably up until this year, when she's handed over to Sanaz, who has ably stepped up into that role. Their professionalism and quiet mode of prompting and delivering has meant it has been a joy to work with them. So as the PRIF Consortium concludes, you should all be proud of what you've achieved. I hope you've learnt a lot, developed relationships and connections that you will take forward into the next phase of your careers. For me, it's been a pleasure to chair the governance board since its inception. So thank you for providing me that opportunity. I wish you all the best for the remainder of your work with the PRIF and into the future. Thank you.
So now we may have time just for one or two questions, if there is any in the room. Looks like no. Okay, if no more questions, on behalf of all of us in the PRIF.
Yes, Anas, let me just use this opportunity, please, to thank you and Tatiana for all your immense amount of work that's been involved in putting this together today. It really would not have happened without you two working incredibly hard, and a number of other people as well, but I mean especially you two over the last month or so. I just say yes or no and maybe and whatever. You actually get on and do all the things, all the agendas, all the emails, the invitations, everything else. So it would not have happened without you. We are very, very grateful. Thank you.
Thank you. Thank you for your support. Thank you, Nigel. That's nice of you. So on behalf of all of us in the PRIF, I would like to thank you for your attendance and today's conference. I hope you enjoyed the talks. And now you are invited to have a drink with us and enjoy the networking session in this room. Thank you.